Good morning, students. In this class, we will study about signal flow graphs and Mason's gain formula. So, this is a very important formula. So, I put it in the title slide itself. It's very important. So, we'll learn this formula. Okay, let me highlight this. So at the end of the class, you should be able to use this formula to find transfer functions of not very simple system. So for block diagram reduction, you saw that it's interesting. It's a puzzle in itself. But signal flow graph and Mason's gain formula helps you to do it in a very systematic manner. Okay. So and it's kind of easy marks for you for the examination. What is the significance of signal flow graph? We have seen that block diagram is tedious. It was introduced by Mr. G.J. Mason. It is easy and convenient. You can represent set of simultaneous linear algebraic equation. A lot of advantages are there for signal flow graph. So let us look into the major terminology. It's very easy, okay. I'm sure that if you watch this video, you will be able to do any problem in Mason's gain formula. But block diagram reduction, even if you do 10 problems, maybe you may not be able to solve some problem. So study this systematically, it will benefit you, okay. But the point is, you should know some terminologies. You should know what a node is. A node in a signal flow graph represents a variable or a signal, okay. So branch, you have two nodes and there is a directed line connecting the two nodes. It's called a branch. Input node. In a signal flow graph, there will be many nodes. One node is the source node from where everything starts. It's called the input node. Output node, node that has only one incoming branches. A node that has only incoming branches are referred to as sink or the output node. So that is where the SFG ends, okay. Now these are not very hard, okay. So all the other nodes are mixed nodes. There will be signal coming and signal going out. So in short, what is an input node? Input node is a node from which signals are coming out, okay. It's a source. And output node is where the signal come and kind of ends. There are no outgoing nodes, there are only incoming branches. So such node is called output node, and all the other nodes are called mixed nodes. So here I have given a very simple signal flow graph. So this is input node, okay. You can see that only signal is coming out of this node. What about this node? This node is output node. N1, N2, N3, N4 are nodes, and there's a line segment joining N1 and N2. This is one branch. This is a branch. This is another branch connecting two nodes. This is a third branch. All of this branch I used red color, okay. So you know now nodes, you know branches, you know input node, and this node is what? N2 is what? It's a mixed node. N3 is also a mixed node. So nodes I have marked it with yellow. So I'll repeat here. Nodes represent variable or signal. Branches join nodes. So when a signal goes through a branch, it gets multiplied by its transmittance or gain. We'll see that in the next slide. So here we saw that N1 is a node, N2 is a node, N3 is a node, N4 is a node. And we saw that N1, N2 is a branch, N2, N3 is another branch, N3, N4 is also a branch. N1 is input node, N4 is output node. What happens? Let us see. Transmitting. The gain acquired by the signal when it travels from one node to the another node is called transmittance. So this has to be explained. Okay, so now things should be clear. Here, suppose the signal here is X. When it goes through this branch, it gets multiplied by 1. So here also it will be X. When it goes through this branch, what happens? When it goes through this branch, the signal will get multiplied by K. So what will be the signal available at N3? The signal available at N3 will be K into X. And what will be the signal available at N4? Again, signal available at N3 into 1. So that also will be equal to K into X. So I hope you understood the terms node, branch and transmittance. A path, a traversal of connected branch in the direction of branch arrows. So here in this simple diagram there is only one path. So this we call a path. So signal coming over here travels through node N2, N3 and N4. These are easy. Once we do few problems, these will become very clear. Okay. Forward path. Path from input node to the output node and does not cross any node more than once is called a forward path. So in this simple signal flow graph, there is only one forward path. The signal coming over N1 will travel from N1 through N2, N3 and will reach N4. So that is the forward path. What's a closed path? It start and end at the same node. That kind of path is called closed path. Is there any closed path in this diagram? In this diagram, is there any closed path? No. So let me pause. So let us go to the next slide. Let's go to the next slide. So loop, a closed path starting from a node after passing through certain part of the graph arrives at the same node without crossing any node more than once is called a loop. So closed path and loop is somewhat very similar. The main difference is a loop will not visit a node more than once. Loop gain, product of branch transmittances of a loop is called loop gain. As I told you, don't worry about these definitions. Once we see some illustration, things should be very clear. Non-touching loops. If loops that does not have a common node, they are called non-touching loops. So let us look at this example. Identify paths, loops, nodes, non-touching loops, if any, in relation between as far as signal flow graph is concerned. So let us identify the path. How many nodes are there? This is one node, x1, another node, x3, x4, x5, x6, x7, x8. What are the input node? What is the input node? x1 is the input node. And what is the output node? x8 is the output node. All the other nodes are mixed node. What are the loops? So let us look at the definition of loop. So loop is a path which starts from a node and reaches back the same node without touching any node more than once. So let me choose a light green color. This is a loop. Why? Because it starts from x3, goes to x4. So this is a loop. What about this? Is this a loop? G1? Because G6, you see the arrow in G6 is in this direction. So G1, G6 is not a loop. What about this? G4 minus G8. This is also a loop. What about this? G5 and 1. This is also a loop. So how many loops are there in this problem? There are 2 loops. How many non-touching loops are there? If I call this loop L1 and this as loop L2 and this third one as loop L3, L1 and L2 is non-touching, L1 and L3 is non-touching. What about L2 and L3? It is touching. Why? Because node X6 is in common. So let us go to the next slide. How many forward paths are there? So how many forward paths are there? So this is one forward path. Is there any other forward path? There is one more forward path which is along G6. So one forward path is having a gain 1 into G1 into G2 into G3 into G4 into G5. Another forward path is having gain 1 into G6 into G2, G3, G4, G5 and 1. So there are 2 forward paths, 3 loops and 2 pairs of non-touching loops. I hope it is clear. So it is applicable to linear time invariant systems only, signal flow graphs. For a given system, you can draw many signal flow graphs. It's not unique. A node in a signal flow graph represents a variable or a signal. Node adds the signal of all incoming branches. So that requires some explanation. Suppose this is a node. This is a node. One signal is coming over here. If this signal is x1 and another signal is coming over here, it is x2. And if I draw 3 arrows like this, then from the context we should understand that 2 branches are input branches and 1 branch is outgoing branch. So node adds all incoming branches. Suppose the signal coming over here is x1, signal coming over here is x2, the output signal will be x1 plus x2. So this is very important. Branch indicates the functional dependence of one signal on another. Signal travels along the branches only in the marked direction and gets multiplied by the gain of the respective branch. Suppose here I have x1 and gain is g here, and here it is x2, and gain is 1. So what will be the signal coming over here? It will be x1 into g plus x2 into 1. So that is what is meant by here. Signal travels along the branches only in the marked direction and get multiplied by the gains of the respective branches. We'll have some examples. So how many nodes are there? This we have seen earlier. I'm saying again, nodes, there are 4 nodes, n1 to n4. So node represent signal. Here it is, suppose here it is x, the signal over here will be x itself, here it will be k into x. And how many branches are there? 3 branches. We have seen this already. If signal here is x, if signal at node n1 is x, then signal at node n4 will be k into x. So this I have scribbled down a figure there. So let us look at it closely. Write the equations for x4 and x5. So let me highlight x4. This is x4. So what are these signals? x1, x2, x3. So signal x1, x2, x3 is coming to node x4. What happens? Signal x1 will get multiplied by A, signal x2 will get multiplied by B, and signal x3 will get multiplied by C. So what will be the signal at x4? It will be AX1 plus BX2 plus CX3. So here it is written, x5 is AX1 plus BX2 plus CX3. Why nothing happens over here? Because the gain is 1. Because the gain is 1. Write equations for y, z1 and z2. Here, let me use another color. Here this is y. This signal is x. So what happens to x? It gets multiplied by g. So y will be what? Y will be gx. And what will be z1? All signals going out of y will be the value of all signals coming into y. So z1 is gx, z2 is gx. So what about this? So this is interesting. So x3, y1 and y2. This is x3. What is x3? A into x1, A into x1 plus B into x2. You remember I emphasized in the last slide, if you have a node and many signals are coming to that node, it adds up all that. So what will be x3? x3 will be A into x1 plus B into x2. And what will be y1? y1 will be g into ax1 plus bx2. And what will be y2? y2 is getting multiplied by g2, g2 into ax1 plus bx2. So remaining we will see it in the next class. So thank you very much.